There are many ways you can configure the 555 timer as an oscillator. We'll begin with what is probably the very simplest oscillator circuit there is with the 555 because it really only requires two external components to implement the oscillator itself. You will have the bypass capacitors, as I mentioned in the overview video. Never forget those. There's also a small capacitor connected to the control input, which is the point in that voltage divider that is nominally 2/3 of the overall power supply voltage. The purpose of this is simply to stabilize that voltage, to keep glitches off of it, and make sure it really does remain at the desired value. You could probably get away with not including this little 0.01 microfarad capacitor on the control input, but this is just standard procedure to stabilize that point. So go ahead and add it unless there's some real good reason not to. If we look at the circuit with the 555 just drawn as a box, you can see that it is fairly simple. There is a timing resistor and a timing capacitor. Note that the discharge pin, pin 7, is not used in this case. It's kind of difficult to just look at this picture and see what actually happens, so we're going to look at the same circuit, except we're going to expand the 555 into its block diagram. Let's start by assuming the timing capacitor down there at the bottom is initially discharged, and we'll assume that we are running this between ground and some positive voltage. So we'll assume that that timing capacitor is initially discharged. If it is initially discharged, note that the trigger input, the inverting input to that lower comparator, is less than that lower voltage divider point, which is nominally 1/3 the power supply voltage. Since it is less than that, that comparator goes high. Since the set input is high, the flip-flop goes high. The final output after that pair of inversions goes high. And so the timing capacitor starts charging toward the output voltage through the timing resistor, R sub T. Now, one thing that I have not yet mentioned is that as far as the output voltages for the 555 go, the low state output can get within about 1/10 of a volt of the lower power supply limit. If it's ground, that would be about 0.1 volts. If you're asking that output to sink a lot of current, say more than 10 or 20 milliamps, then it can sink a lot more than that. It doesn't have the same limitations that most op-amps do. It can sink or source a good bit of current, but if you ask it to sink a lot more current, then that voltage is going to tend to drift upwards. When the output goes high, it is about 2 diode drops below the upper power supply limit. Most spec sheets show that it's about 1.6 or 1.7 volts below the upper power supply limit. And we may look at the actual internal circuit diagram of the 555 at some point, and you'll see why that is true. So, the output goes high when the capacitor voltage is really low, and the capacitor starts charging up. Eventually, the capacitor voltage passes 1/3 VCC, so that lower comparator then turns off, so the set signal goes away. But nothing happens because it's a flip-flop. It remembers what it had last done until it gets a command to do something else, so the capacitor keeps charging up. The output stays high. Eventually, however, the capacitor voltage reaches 2/3 of VCC. Now, when that happens, that upper comparator turns on, and when it hits reset, the output goes low. When the output goes low, all of a sudden, that capacitor is at roughly 2/3 of VCC, but it sees a value very close to ground on the other side of that timing resistor, R sub T, and so it starts discharging. When it starts discharging, that threshold voltage at that upper comparator almost immediately goes below 2/3 VCC, so the reset signal disappears. But again, it's a flip-flop, so it's going to remember its state until you tell it to do something different. So the capacitor continues to discharge, and eventually it reaches 1/3 VCC. The bottom comparator turns on, it sets the flip-flop, and the whole process starts over again. You might note that this circuit is really effectively an integrator Schmitt trigger oscillator. The two comparators with the associated resistors and the flip-flop form the Schmitt trigger, and the timing resistor and the timing capacitor form an integrator, which is basically integrating the output voltage. Now, that's not exactly perfect because it's actually charging that capacitor exponentially, not linearly like an integrator would. But the operation of this is really very similar to the integrator Schmitt trigger oscillator that we saw built with operational amplifiers. As far as the frequency of oscillation of this circuit goes, that can be calculated as approximately 0.66 divided by R sub T times C sub T. Now, we're not going to do that derivation here. I might do that in some future video, but not right now. Note, however, that you can easily make the frequency of this variable by replacing the fixed resistor R sub T with a variable resistor. And you can very literally vary the frequency of oscillation over a few orders of magnitude with this. In the next few videos, we will look at some modifications, enhancements of the simple oscillator. And again, we're only going to scratch the surface on this. We can't possibly cover all possible permutations of the use of the 555 as an oscillator.